Next, as we have studied that electronic configuration of the atoms of lanthanides, they have 6s2 orbital in common, but they have variable values of 4f orbital, right? How the variable value for 4f orbital? The value of 4f orbital, it varies according to their atomic numbers, right? Now, if we talk about the atomic and ionic sizes of lanthanoids, so it is clear now that lanthanoid contraction, where the atomic as well as ionic radii decrease, okay, with the increase in their atomic number, okay. So that is why, due to the gradual decrease in their atomic and ionic radii due to poor shielding of 4f electrons or 4f orbital, right? The lanthanoid contraction takes place. Now, with the increase in atomic number, the nuclear charge increases, and that means the electron being added to the 4f orbital. Okay. Now, this results in distorted and diffuse shape of 4f orbital. Okay, and that causes the poor shielding of 4f electrons. All right. So, right now here one question arises, which have been asked in exam, that why zirconium and hafnium element they have similar size, right? Now, while moving from zirconium to hafnium in lanthanoid series, all right, there is a difference of 14 elements in them, but still they have the similar size. Now, what is the reason for that? Now, zirconium and hafnium, there is very slight difference in their atomic radii, that is 160 picometer, right? Now, when we move from zirconium to hafnium, okay, 14 elements are present in there, okay, and the atomic radii, as it mentioned here, that is 160 picometer for zirconium and 150 picometer for hafnium. That is almost similar atomic radii, right? So due to which their 4f filling, 4f orbital filling is the reason, okay, that why their size, it does not increase, right? So owing to the 14-15 electron and the electron in 4f orbital, which has poor shielding effect, they are found to have similar atomic radii, right? As a result, lateral contraction, the elements of second and third transition series, okay, they bear striking resemblance. All right. Now, if we talk about the oxidation state of lanthanoids, with plus 2 and plus 3, they are the predominant species that in lanthanoids with plus 2 and plus 4 ions in solid or solution. Basically, if we look at this table, we see the lanthanide, they show the plus 3 oxidation state. Okay, so they can exist between plus 2 to plus 4 oxidation state based on some good oxidizing or some good reducing agents that are present in lanthanoids. Okay, which are some exceptions that we will study also, but commonly they exist in plus 3 oxidation state, right? Now, what are the exception on the basis of the oxidation state of lanthanoids? Okay, so first exception is cerium. Okay, cerium, if you can see here that cerium exists in both with atomic number 58, it exists in both plus 3 and plus 4 oxidation state, right? Now, cerium, its electronic configuration is 4f2 and 6s2, right? And it exists as plus 4 oxidation state, okay, rather than the common oxidation state shown by the lanthanoid as plus 3. Okay, this question have been asked in exam like many times, that why cerium shows +4 oxidation state rather than the common lanthanides oxidation state +3, right? Now the reason for this is that cerium is a strong oxidizing agent. Okay, with +3 oxidation state, it is a strong oxidizing agent. That is why, so the first reason is that it is very good oxidizing agent. Okay, and because it can go in reduction as well, and ends in +4 oxidation state of lanthanoid. All right, so it can show both reduction as well as oxidation, and can exist in +3 and +4 oxidation state. All right, so this is the reason that cerium exists in +4 oxidation state, right? Other than that, we have exception of euphorium and ytterbium. Okay. Now euphorium here is having atomic number 63, okay, with electronic configuration of 4f7 and 6s2. Okay, so these electrons, it can be removed easily, right? So euphorium also, it exists as euphorium 2 positive, right? And with the with the loss in electron, it can attain euphorium +3 oxidation state, right? So it is a good reducing agent. Okay, so that is why the oxidation state for euphorium, it varies from +2 to +3. Okay, so if the question arises like mainly the lanthanides, they are having +3 oxidation state, and if the question arises that why euphorium or ytterbium, they are showing +2 and +3 oxidation state, that is because that they are good reducing agent. All right, and as well as if we talk about cerium, that is good oxidizing agent, so that is why their oxidation varies from their common oxidation state of +3. All right, so I hope the oxidation state of lanthanoids is clear, right? So moving on to the general characteristics of lanthanoid, okay, where we will sum up what we have studied, or the what type of lanthanoid metals are, what are the characteristics of lanthanoids. So lanthanide, first of all, they are soft metals and of silvery white color, and that get easily tarnished even in the presence of air. They have the melting points that lies between 1000 Kelvin to 2000 Kelvin. Okay, and they have generally trivalent ions. By trivalent ions, we means that their oxidation state, it generally lies in +3. Okay, and as we have discussed that lanthanoids, they are all paramagnetic. How they are paramagnetic? If we try to fill the 4f electrons, how many electrons we fill in 4f? 1 to 14, right? Now if we try to fill the electrons till 7, as they are unpaired, they will show the paramagnetic behavior. And even if we try to pair them till 13, so the last electron, it will remain unpaired. So that means that till 13 electron, the lanthanides, they generally behave paramagnetic. Okay. Talking about the ionization enthalpies, the first and ionization enthalpy, they're given here. Okay. And they are having generally high ionization enthalpies due to their smaller size. All right. Due to their smaller size, their ionization enthalpies are high, their nuclear charge decreases, Nuclear charge decreases due to they have success to small size orbitals, all right, and have high ionization energy, okay, and they are less metallic in nature, all right, and due to poor shielding of 4f orbital, right, so their first and second ionization enthalpies, it varies, all right. The low value of third ionization enthalpy of lanthanum and gadolinium and lutetium is due to the stability of empty or half-filled f orbital that we have discussed. All right. General characteristic and comparison with lanthanoids. Here we have compared the characteristics of actinoids and lanthanoids. Okay, actinides also they have silvery white appearance. Okay, and have these structures that are irregular in their metallic radii. Why they have irregular structure? Due to the actinoid contraction that we observed based on the atomic and ionic radii, okay, or the atomic sizes of the actinoids, right? Now, actinides they are highly reactive. Why? Because after 92 atomic number, all the actinoids they are also radioactive in nature, right? So they are highly reactive and they produce a mixture of oxide and hydroxide when reacting with boiling water. Okay, all the metals they are attacked by HCl but slightly affected by nitric acid, and they form. This is about the reactivity. Okay,